Alrighty, folks. So I have gotten a number of questions about how to complete the Module 9 Activity Points worksheet. And so I'm going to go through an example in this video to hopefully help clarify what exactly we are going to be doing and how we are going to be completing um, these questions. So, as you can see here, I have partially filled out a chart. I am just going to go through tongue rolling as an example, but know that you will complete these calculations for each of these traits in the chart. And now in my example here, we have recessive traits, meaning that people cannot roll their tongue, and dominant, meaning that people can roll their tongue. And as we can see here, as I've labeled the dominant and recessive traits, we have a capital R dash for a dominant trait of someone who can roll their tongue. Reason being is because we just know that they can, but we don't necessarily know that their genotype is homozygous or heterozygous. But the good news is that we do, in fact, know when a person cannot roll their tongue, they must be homozygous recessive. That's kind of how all of this works. And so the first question is asking us to tally up each trait to figure out which are dominant and which are recessive, and that our calculations should equal 10 because we have interviewed 10 people. And so I'm going to write out dominant versus recessive. And you can see here I have 1, 2, 3, 4, 5, 6, 7 individuals that were dominant and 3 individuals with the recessive trait. And sure enough, my totals are equal to 10, so the math is mathing. Now, what we need to do is figure out the percent of individuals that have the recessive trait, the dominant trait, and we can actually utilize the Hardy-Weinberg equation to figure out which of these people are actually heterozygous dominant versus homozygous dominant. The equation is written down here where a P is equivalent to a dominant allele, and a Q, which I guess is opposite of a P, is the recessive allele. And what we know is that the presence, or like I guess the percent ratio of P alleles and Q alleles should equal 1, or essentially 100%. But each individual will have 2 copies of these genes. And so how the Hardy-Weinberg equation works is we write these brackets around that original equation and we put it to the second power, basically emphasizing that everyone has these 2 alleles. But as it turns out, this is still going to equal 1. If we write this out longhand, this is just going to be some basic algebra, we end up with the following. P squared plus 2pq plus q squared equals 1. And now this is looking specifically at our genotypes. So this p squared represents homozygous dominant. This center component represents our heterozygotes, or people who are carrying the recessive trait. And then our Q squared is going to be people who are expressing the recessive trait or are homozygous recessive. And now, unfortunately, we don't have a clue what is going on with the dominant traits genotypes. And so we can't really calculate our P's just yet, but we can start by calculating our Q. Now, right here, we have a Q squared, and we actually can figure out what percentage of people have this particular genotype. So what I'm going to do is I am going to look at the recessive versus the dominant individuals distribution. And I know that there are 3 recessive individuals over a total of 10, which is the number that I gathered, which that is going to be equaled to 30%, or another way to say that is 0.3. Now, this number right here is in fact our Q squared number. So that is going to be equal to the percentage of people who are homozygous recessive. In order to solve for this Hardy-Weinberg equilibrium equation, we need to figure out what just regular Q is. In order to do that, I'm going to take the square root of both sides, and as just basic algebra is stating, Q squared, the square root of that is going to give us Q. And if I just type the first part into my calculator, Q is going to be equal to 0.548. And I'm doing a little bit of rounding here. So now we actually have the percentage of the Q allele present in the population. If I were to go and use this first equation, I also can figure out the percentage of our dominant allele. And this is just going to be some simple math as well. I'm going to basically plug the numbers into my equation and do a little bit of rearranging, essentially saying 1 minus the number I just got, which is 0.548, is going to be equal to P. And if I were to just plug that number into my calculator, I also can figure out that means that P is equal to 0.452. So that's awesome. Now we have basically everything we need in order to finish our equation. So if we are looking over onto the equations, we can now figure out the carrier frequency of our trait, because we have what both P and Q are equal to. So if I were to take this equation, I could say 2 times our P value, which is 0.452, and then multiply that times our Q value, which we know to be 0.548. That is going to give us the percentage of 0.495. Now, don't worry, I have done these calculations beforehand. I'm not all just doing this in my head. We can also calculate the first part of this equation by taking our p-value and squaring it. So if I were to do that, that is going to be 0.452 squared, and that number is going to be 0.205. And so this is a lot of math. These are a lot of numbers. And so what I'm going to do is I'm going to rewrite some of this just so that it's a little bit clearer. So what we have is our p squared value, which, remember, that is going to be the percentage of homozygous dominant individuals. That number we've just calculated. That is our 0.205 or essentially, that's saying like 20% of the population. 20.5. Our 2PQ value, so this is representative of the dominant individuals that are carriers for the recessive gene. And this number, we've also already calculated, that was that 0.495 number, which is equivalent to 49.5%. And the very first number that we calculated was our Q squared number. And we knew that was 0.3, which is equivalent to 30%. And now, if we were to add all of these numbers together, so adding up our 0.205, our 0.495, and our 0.3, and plug it back into this original equation, what we should end up getting is a total of 1, which we do. So now I can look at that and say, great, I have done my math properly, and I've figured out the frequency of these different traits. We've figured out the dominant trait frequency, the recessive trait frequency, and the carrier frequency. Hopefully this video helps.